Okay, so let me give you another example of this. Don't think I have enough space, so let me just delete everything I have here and give you another page. So another example, let's look at the Bernoulli beam equation. So the Bernoulli beam equation is actually very similar to the Poisson's equation, except for there is a fourth derivative. Okay, plus f equal to 0. How many of you have seen this equation? Oh, okay, pretty much a lot. So basically, W is the deformation of a beam, and F is the force you apply transversal to the beam. Okay, and that equation basically tells you how the beam is going to be deforming. And for the beam to be having a unique solution, you need to have boundary conditions, right? So for example, if I clamp both sides, which means I do not allow either side to deform, I also don't allow either side to rotate. That means I have a boundary condition. So let's say this is within the space of 0 and 1. The beam has a unit length. I have W0 equal to W1 equal to 0, right? Is that all? Do I need additional boundary conditions? Huh? The gradient, right? So I also need the derivative of W to be 0. So that is basically a beam. Let's say this is 0, 1. A beam that can be deforming whatever way I want, but like at the end is clamped so that it's not only not allowed to move, it's also not allowed to rotate freely. So it cannot do something like this, right? So basically it's clamped. If it's allowed to rotate freely, the correct boundary condition has to be the second order derivative is equal to 0, right? Because it has no torque at the ends. Okay, so let's see if we multiply this equation with a test function v, how do we convert that into a weak form? Okay, so same thing. If I multiply that equation with a test function, it's still supposed to be equal to 0 everywhere. And I integrate a 0 function, I'm supposed to get a 0, right? Okay, so let's see. Immediately we see the second term v times f is going to fall out as a linear form, right? That has nothing to do with w. It serves just as the right hand side. Okay, but the first term we have to do integration by parts to get a symmetric bilinear form, right? So basically what's special about this a here is not only it's bilinear but also it's symmetric, right? So this a of w and v is actually the same as a of v and w. So let's see, how do we get to that stage? Okay, how do we get to that stage? It's again integration by parts, right? So let's do our first integration by parts. We have, okay, so let's actually list the boundary term first. V times what for the boundary term? Yes, the third derivative of w. 0 and 1, okay, and minus integration of the first order derivative of v times the third order derivative of w. Let's keep the v times f to be here. All right. Somebody tell me what to do next to get a symmetric form for a, for the bilinear form that involves both w and v. Do it again, yes. Okay, so let's actually do it again. So keep this here. By the way, you can see from the boundary condition that v has to actually satisfy the same boundary condition, right? So this term actually goes away because v is equal to 0. So now if you do it again, we have the boundary term now becomes minus because this is minus. dv dx now times the second order derivative of w at 0 and 1. Plus, now because we have two minus signs from the double integration by parts, we have, okay, so write v first, the second order derivative of v times the second order derivative of w. Now we get a symmetric form. right? And this boundary term again is equal to 0 because of the derivative boundary condition, right? Okay, so that way we get basically 2 zeros. And by the way, if you instead having the first order derivative boundary condition, if you have a second derivative boundary condition, this also cancels, right? Because the second derivative of w is involved over here. So now we ended up having a weak form like this. So here we have this being our a of vw. It turns out to be positive definite plus b of v equals 0. All right. And actually the convention is if we actually get a negative definite a here, we actually put a minus sign here. So basically make it positive definite. So if a of u is always greater than 0 unless u is equal to 0, that means it's positive definite. Right? It's like a positive definite matrix in some sense. So actually a positive definite matrix is a special case of a positive definite bilinear form. It just operates on 2 vectors as opposed to be 2 functions, right? So you have a matrix, you left multiply a matrix, left multiply a vector, you right multiply a vector, you get a number, right? So basically a matrix in some sense is actually a special case of a bilinear form. Just not apply to functions, apply to vectors. Okay, any questions on this?